So let's start today's lecture. First, let me share the screen. Okay. We will gonna to continue the part we didn't finish in our last lecture. First, we need to connecting again the notebook and then we will rerun the previous code. Okay. We install the libraries again. And then we import all the packages. Seems that there is a conflict between the packages. Let's ignore it right now to see if it will cause some errors. Now we will loading the data. We pre-download it. So we read and resemble this pre-downloaded data into our working files. Wait a few seconds. Once it's finished, we can find the file here, and this one will disappear. Okay, now it's completed, and we will read the wind speed into our memory. And then we calculate the wind speed. I will be very quick because we already mentioned all of this part in the previous two. And we just running cells, cell by cell. Okay, now we get a time series of the maximum wind speed. And then we can skip the plot. We calculate the annual maximum. Also, okay, we don't need to plot, but we can calculate the statistics. And we can skip this part. But we will need the empirical way, the result of the empirical calculation. So we run this step to get this plotting position. And We can fix our distribution, fit our distribution. First, the dumbbell one, and we can skip the evaluation. And then we fit a GV without assumption. We got all the parameters we have. And now we arrive here. Yeah. So last week, we stopped the lecture here. We already fit two type of distribution. First, the dumbbell one, and the other, the GEV. You can see for each fitted distribution, they have their advantage and disadvantage for fitting the real position of the observed wind speed. Now, we can do a quick comparison. Here we can see, first, let's say why the GV is better model in our case, like compared to the Gamba. Because the best fit for model doesn't mean that it perfectly fits every observation or data point. Instead, it means that the model, in our case, the GV, it better describes the statistical properties. And then it's not holistic fit all the data points. The nearly straight line on the GV QQ plot, as we mentioned before, demonstrate that it can successfully capture the overall behavior, the pattern of the data, but you can find in that plot, there are some parts, especially for the tiles of the observation data, has a significant bias. So the fundamental assumption for the dumbbell, like the shape parameter equal to 0, may be incorrect. Therefore, from a statistical point of view, the GV is more validated in our case. And then, if we are trying to force a model to perfectly fit every data point in the observation point, we might have a risk of overfitting. Because such a model might be perfect when you are fitting within observation data, but might be biased in its future predictions. Because it gives too much weight to this kind of few observation random extremes in our specific samples, rather than capturing the long-term behavior of the system. And then, in the parameter fitting process, our model parameters, the mu, the sigma, the c, are derived using optimization algorithms in the packages. Like here, we use the maximum likelihood estimation that they consider all the data points rather than some few extremes. The goal of these algorithms is to find the set of parameters that maximize the probability of observing the entire data set. So not specifically for every data point. So it's like a group decision. It's listen to every data point. For example, one or two loud points, in our case, some very extreme points, cannot dominate the final outcome. That's why the reason there's still some bias for estimating the very extreme points. And this case study can serve as an example for explaining the different facts of uncertainty. In our case, we actually face the model uncertainties. By choosing the GV model, or Gumbel model, we have reduced the model uncertainty because the GV model is better than the Gumbel one. We select a model that is more flexible and in practice has proved to have a more appropriate distribution shape by our observed wind speed. And there are other sources of the uncertainty. For example, the parameter uncertainty, when we fit a distribution, we estimate the parameters based on our current data set. If we had the data from a different 75-year period, or different data points, or different station location, we would like to get a different blue line, so different fitted line. In a more robust analysis, we should plot the confidence intervals around the GV lines, but it's not the purpose in our study. And then we could find the random and sampling uncertainty. The event we observed in 1973 is the largest event in the observation dataset, and it could be just one random realization of a 100-year event. For example, a 100-year event might be larger than this event because in the real world, it might only be a random realization. And the model's objective is to estimate this average behavior, not to perfectly replicate every single random observation. And the fact that the GV model slightly underestimates these 2 points is what we can expect it. And because it's the model is a simplification of the reality, and it cannot reproduce every observed event. And so far, we looked the Gumbel model and the GVM model separately. We draw a conclusion that in our case, the Gumbel overestimates the risk, while GV provides a much better fit, but it still slightly underestimates the 2 most extreme events. Now, we can put them all together in one plot and to compare its behavior, okay? We run this cell. Okay, it shows that the ticker is not defined, so we can import that. No, we from that ticker import ticker empty. Still doesn't work. Let's try because it was imported in the previous party. Let's try to find where is it. Still not. Okay. Import as. Okay. Now it's okay. We can see from this plot. Now, what is shown in this plot? We put the empirical with a plotting position, like the dark dots, and the GV fitted line in the blue line, and also the Gumbel fitted line, the orange line. We put them all together, and what we can see here, for the return periods of 50 years or more, you can see that our empirical data points They are nearly between the Gamble line and the GB line, like in these dots. They are not perfectly on each line, but it's located in between the range of these two lines. This leads to a crucial insight. Like instead of giving or selecting which single line, like which single distribution is correct, what if we interpret the space between the two lines? Like we interpret the range between these two lines as the plausible range of uncertainty. What does it mean? Like if I ask, what is the 100-year return level wind speed? So in our result, the GB model will give us one number here. In the GB model, it will give us a number around 16.8, right? In this point. And in the Gamble model, it will give us another model. It's a higher number. Higher number, it's around, it's more than. It's around 18.2. Sorry, I need to modify here, like 18.2. And both of them are single point estimate. I estimate a point here from GB and another point here from the Gamble. But this chart allows us to change the question. Instead of asking the correct number, because we can have a range here. What we can be asking, what is the possible range for the 100-year wind speed? Based on our analysis, we can give a much more honest and even more useful answer. Like our models, our analysis shows that the 100-year wind speed is most likely around 16.8. But given the uncertainty, our modeling uncertainty, a plausible range could extend up to still 18.2 here. Now we are not given a specific number of the wind speed, but we can report a range of the possible wind speed for a 100-year event, okay? Because you can see all the observed events, it's located within this range in this case. So what we are talking about is the model uncertainty. So the GB line represents our best, most flexible model, and we can consider it as our best estimate. And the Gamble line represents a simpler, more rigid model. In this specific case, because it consistently overestimated the risk compared to the better fitting GB, we can think of it as a conservative estimate or upper boundary. So it can serve as an upper boundary of our risk, of our estimates here. So by presenting both the results, we are transparently communicating that our final prediction is sensitive to the assumption you make. What's the assumption you make here is that first we assume the observed data fit a Gamble distribution, or we assume the GV fit assume the distribution fit a GV distribution. Okay, that's the assumption we make for the real world distribution. And why does this matters for the decision making? For example, imagine you are an engineer who will be design the Strait of Messina Bridge. For example, if we only use the GV value, so the lower line, we might design to a standard. It's very robust, but potentially it's very robust for most of the case, but it's potentially is not conservative enough for very critical extreme events like the 1973, because it will underestimate the most extreme event if we only rely on the GeV distribution. What if we only use the Gumbel value, so the upper line? We may be over-engineering all the time. Like we may over-engineering, because we design for even more extreme situation that the real world could be. For sure, it will be more safe, but we will spend millions of dollars more than necessary. So this range gives us a sense, but it doesn't have a very strict statistical significance because it's not a confidence interval which has a statistic meaning. Scientifically, we have a more standard method for quantifying this kind of uncertainty of our best model, in our case, the GV model. For example, we can calculate the 95% confidence interval based on our GV model when we are fitting it. For example, we can do some bootstrapping, this kind of algorithms, and then it will have a confidence range of, give us a range of the 95 confidence range that the data will have a 95 confidence probability that located in that range. It will tell us the true because we have give the limitation of our data, there is a 95 chance of that true 100-year event will fall within this range. So for example, here we have a GV feed, and then if we will have a 95 statistic confidence interval, it would be like a line here in the upper boundary, and then we will have also a lower band here. In general, in our case, I think it will cover all the observed data points. Oh, that's important. In general, when we communicate to the decision makers, it's better to communicate the range with the uncertainty estimate rather than just give them a number, because there is no best model which can really represent the real world case. Remember that every model is just a simplification of the real world. Okay, that's all the parts about how we can download the open source wind speed data from the Copernic data stores, and how we resampling the daily wind speed into the annual maximum, and how we estimate the return period from our annual maximum time series. And we can also fit different distributions from different models, and then we compare the model performance, and we get a better model, in our case, the GV models. And the important note, always communicate the model uncertainty. In our case, we only consider the model uncertainty to the decision makers. Finally, here I also prepared a code for plotting the example in introducing the parameter perturbation. Like here, you can plot the GV probability density function, and then in this cell, you can change the different parameters. For example, we change the increase mu here, and we increase sigma here, and finally, we increase C to see how the shape changes. So it's the same figure I used here to illustrate how these parameters will change the shape of the distribution here. Okay. In general, if you have any problem in using this part of the code, just write to me. Okay. Now we are going to move to the second part in our lectures. I think you don't have the link of this notebook yet, so I'll send it into the chat. Okay. I send it into the chat. And in this notebook, you can do the same as the previous one. First example, you can, after click the link of the notebook, you can save a copy in your driver, and then you will be able to run in the cells and also modify the text and codes within this notebook. And this notebook, I will give a brief introduction to the CMIP6. It's the latest global climate models. And then we will do a case study of the wind speed changes for the Strait of Messina Bridge in the future. Okay, first, what is global climate model? I think all of you have heard about the concept. And in general, the global climate models, they are also called general circulation models, means it solves the atmospheric circulations. They are numerical models that simulate the behavior of the entire system. And they solve the physical equations for how air, water, energy, and momentum move, and their interaction in the atmosphere, ocean, land surface, and cryosphere. So all the general components in the system. And the key characteristics is that it's physical based. They are not just a statistical fit to the past observation data. They are trying to represent all the underlying process that drive the climate. And then it's 3D and fully coupled. For example, a typical GCM divided our planet into a 3D grid for the latitude, longitude, and also the vertical levels. The model steps forward in time from minutes, but in general for the global climate models, they are from hours, daily, monthly, and annually. They were updating all the essential variables like temperature, winds, humidity, ocean currents, and clouds, etc. Many modern global climate models, they are coupled model. What it means coupled model? It means that the different components inside the model, like the atmospheric, ocean, sea ice, and land. They are exchange the fluxes of heat, moisture, and movement. So these different components, they are interacting. So they will have the interaction within the model. And the other important character is the forcing and the feedbacks. In the global climate models, in general, it includes external drivers. So what is the external drivers? The external drivers is like outside the nature itself. For example, here, the greenhouse gas emission and the aerosol, the solar changes, and also the volcano eruptions. Okay, and also the internal feedback. The internal feedback is the water vapor, the albedo from the snow ice cover and the clouds. And this means that they can be used both to reproduce past climate and to explore what if futures. What does it mean? Like we can force the models, given that we have an estimation of the future greenhouse gas emission and different futures conditions to see what the climate will be in the future. And why we use the climate models? Because we will need the climate models to attribute what is the dominant factor of the past warming. Is human activity or the natural cases? And then we can use their future projections to see what will be the future temperature, precipitation, sea level, and also extreme events. And finally, we can also use it to study the mechanism in the climate system, like we can study the monsoon shift, also the jet stream changes, the heat waves, and different the mechanism underlying these different events. But still, even the latest CMAP6 global climate models, it still has some limitations. In general, the resolution is very close compared to the local weather because it typically has more than 100 kilometers grid resolution, not locally and not city scale. And the subgrid process, like the conventional and the cloud and turbulent and the vegetation dynamics, it's not fully solved because our understanding about this subgrid process is still lacking and is still very simplified parameters rather than explicitly resolved by some equation. And in different models, they use different parameters. So it will make different model projections, provide different projections. And in general, after the evaluation of the climate models, we will find that there are some bias exist in the models. There will be some warm or cold bias in specific regions, and in some regions, there will be too wet or too dry compared to the observed patterns. So when we use the global climate model output, we often bias correct or downscale them before we do some real impact study in the hydrology, in agriculture, or health, etc. And what is CMAP6? So the CMAP6 is a multimodal experiment. It stands for Carbon Model in the Comparison Project. So it's an international coordination effort by the World Climate Research Program. The idea is that around the world, there are many independent modeling centers. For example, MPI in Germany, IPSL in France, and also here we see CMCC from Italy. They have their own model. And within this project, all these institutions will run their coupled climate models following a shared protocol. So following a shared standard, the same standard. Then they can produce standard output. They will have the similar variables, similar time periods, and also use the same future forcing scenarios. And then all the results are published in a common format. So we can compare all the models in a consistent way because they are running on the shared protocol. And this is very powerful because we can look at a multi-model ensemble, not just one model answer, as we did in the previous notebook. We have multi-models, so we can estimate the uncertainty range from the ensemble of the models, not a single best guess from one model. And then we can check the robustness of the models, like does most models agree on warming in a given region on the different scenarios? Because if we have certain models, for example, in a given region in the Strait of Messina, if all the models agrees on an increasing trend of the future wind speed, we can say that it has a higher possibility that the future wind speed is increasing. And the CMAP6. So here is the CMAP, and the CMAP6, the number represents the sixth phase of the CMAP, and is the generation used for the IPCC report. And is in general the latest climate models that we can use. The CMAP7 is undergoing, but the result is still not fully open access for our use. And here are some core points about the CMAP6. In general, all the models who want to attend the CMAP6, they need to force with the same historical runs with best estimate, observed forcing about the greenhouse gas emission, aerosols, volcanoes, and solar forcing from the late 19th centuries to 2040. It's around 1850 to 2040. So it will be the historical runs for all the models. And they will use to evaluate the model skills against the observations, and then to attribute the past warmings. And within the CMAPs, actually there are lots of different model in comparison projects, the experiment. For example, we will use the scenario maps here. You can see it's the experiments designed for different future scenarios. For different future emission scenarios, and then there will be, and also there are many other experiments like the land use, the land looming. It will be used to attribute the changes related to the land use change. So the focus is different. And also here you can see the ocean, land, and ice. And also here, this one is for the paleoclimate. You can find the climate simulation even for the past 1,000 years, or even to the Little Ice Age, or even earlier. So it's about the past climate. So different experiments have their own focus. In our case study, we are interested in the future scenarios, like the future industry in the Strait of Messina region. So we will focus on the scenario runs. Here is the scenario map. It's based on different shared socioeconomic pathways. For example, these three are the common use. The SSP1 is 2.6. It represents very strong mitigation. So it's the most susceptibility future scenario, and it has a low forcing by 10 to 2,100. And for the SFP 4.5, it's the middle of the road. It's like we keep development, but we have an intermediate forcing. And also we will have a SSP5. It's like the fusel fluid development, and we keep the high emissions and with the high radial forcing by 2,100. And the number actually after the dashed line, the 8.5, 4.5, 2.6, is roughly the radial forcing in watts plus square meter in 2,100. Okay, so it's in general the different future scenarios. And as I mentioned before, the CMAP6, in general, they have a close spatial resolution, but it's better than its previous version. So it's better than the CMAP5. That's why the reason now we generally use the CMAP6 to evaluate their performance and to produce the future projections. And also they are Fourier system models. They include the interactive carbon circle, land use change, aerosol, or the different components in the system, like the vegetation can uptake the carbon emission and also the ocean carbon, and also there are feedbacks. The feedbacks are modeled internally. And for each model, for each institution, they may provide multiple different ensemble members. You will find the same model name, but different initial conditions. Because for every climate models, they will be given initial conditions to force it. And then the climate model will produce the different variables across time. So if you force the climate model with different initial conditions, they will generate different outputs. And this will help us to quantify the internal variability of the climate system. What it means, the internal variability? It means that the year-to-year decade swings in the natural system, because we only change the initial conditions. We didn't change the external forcing when we do this kind of experiment, okay? And why the CMAP6 matters in research, in both research and policies? Because this is the main input for the current IPCC report, and also the National Climate Risk Assessment, and also for the Regional Climate Service. And also it's the source, what we will use to bias correct to produce the regional climate dataset, and also the impact models. For example, we will use them to force our hydrological models to simulate the stream flow for the flood and drought, or we can force it for some agriculture model to produce the projection about the crop yield, and also for the heat streets. And if you ask me how much warming in northern Italy under the SSP5 emission scenario by the late centuries, and we can only give the answer based on this type of climate models. But it's better to give an answer based on all the models rather than one single model. And then we can give a mean of all the models, and then we will have a spread from the 25 quantile percentage to the 75 percentile. And we can interpret the uncertainty range. We should always keep in mind that a single climate model is one classical physical constant climate tragedies. So it only represents one tragedies. And the CMIP6 is kind of like tons of such tragedies generated on the coordinate forcing scenarios. So it's kind of different models provides not all of them, but many of the possible trajectories. And the ensemble is what we actually trust when we talk about the future climate change, and we should always report its uncertainty. We cannot report the results from one single model, okay? And here is the important reference, like the official reference about the introduction of the climate models and the CMAP6 project. And here I also attend to paper about the detailed design of the model experiment and also the parameters. If you are interested, you can have a look into these different references. Okay. Now we will going to not download. I will introduce you a way to access the latest climate models data set, and then to see what will be the change in the future wind speed in the Strait of Messina. We will do the same. First, let's connect to the notebook. Okay, it takes some time. Maybe we can try to refreshing the page. Let's connect again. Okay. Then we will do the same as we did for the first notebook. For sure, we will need different Python libraries. Now you can notice that we, besides the packages we used in the previous notebook, we introduced several new packages. For example, the Java and the data tree and the intake ESM Also here, yeah, as I mentioned before, you don't need to know all the packages, but you should know what they will be used. Like we will use them to deal with. First, to access the data from the climate models, and then we will use these packages to analyze the model outputs. Okay. And then we try to install the package by clicking the running cell. After we finish the installing, we do the same. We will import some necessary packages, and also I forgot to tell you an important thing is that uh, the packages need to be imported before it got used, but it can be imported everywhere in the notebook. For example, before I use the pandas here, I can also import here in this cell, not only here, but it will, why we choose to import here, it will make it more standard, more clean for the users, because we don't need to import the libraries in the following sections. But sometimes we will find that we will need some other libraries while we are writing the code. So it's no problem. We can import later. So we import all of these libraries, and then we will do the same. Not just, well, we will load the data without downloading it. In general, for the climate models, their outputs are a huge amount of the data. It typically count by the units of terabytes. So sometimes it will be very time consuming, and it will cost a lot of our memories in our disks in the working machines. So here I will introduce a way that we don't need to download the climate model output into our dataset. It's similar as what we did to access the error file from climate data store. Like because these kind of data stores, they already keep all the data set there. So we can visit the data, and then we do our own analysis, and we only need to save the result from our analysis rather than downloading all the raw model outputs. So it will be more flexible, and it will save more memories. What we will use is the Google API. I don't know if you have heard about the Google Clouds. We can have a look here. Example, we click, it will be downloaded. We can try to search Google image 6. Okay, here. You can see in Google, they already saved all the dataset from the CMAP6 into their cloud. Okay, so we don't need to download it into our local machine. What we need to do is just to visit the Google's cloud storage. So we can, by using the Google API, you can see from here, what we did here is we visit the description about the entire data set. So we visit this link, the storage Google API and the CMAP6 project, and we visit this. You can consider it like Excel. So the CSV is a data formula, is data format similar to Excel. It stores all the meant data about the climate models within the storage. Okay, we will read it into this data frame. So we use pandas to read the CSV, panda read the CSV into the data frame. And we will print the detailed information of this data frame to have a quick overview about all the models inside this storage. Okay, let's run the cell. Take some time. Okay. Here you can see all the informations within this Excel, and these are all the informations about all the climate models within this storage. Okay. For example, here we can see the activity ID. It represents what I introduced you at the beginning. It represents different experiments, different activities. Okay, we will use this one, the scenario name, in our later analysis. And here you can find the different institution IDs. For example, here the CMCC, and this is the European Community, so from the European. And here the source ID, in general, it represents the name of different models. And here it will be the different experiments. Very detailed example here is the high resolution sea surface temperature present. Okay, and here is the historical rounding for the CMAP. So different experiments and the different initial condition and the table ID in general, it represents different time resolution. So it's atmospherical monthly resolution. And here the variable ID, as its name, different variables. You can find the different variables here. Example, variable pressure, heat, and temperature, precipitation, sea surface temperature, all the variables the climate model produces. And the grid label, in general, it only has two values. The GN and GR to represent different grid type. And here, the Z-store is the link, it's the exactly link what we will use to visit the data. And we will use a packaging to specifically deal with this kind of links. And then it will send our request to the Google store, and then it will return us the data about these climate models. Okay, about all the select activity, institution, source, experiment, member, and table, and a variable. Therefore, the link is unique for each. So after each selection, you will have a unique link for visit. And then this version is in general when the climate model, they produce their outputs. You can find here their very huge amount of the experiments and output here. So for sure, we will not use all of them, but you need to know what you want to do, what you want to analyze. Now, For example, here we know we want to filter the daily surface wind speed under SSP5 future scenarios. Okay, so we will use some filters to filter only the models we need. And here you can find a detailed description about all the activity, institution, and to the degree to version. So for a beginner, you can find a detailed description about what it represents, and then you will know better how to filter what you need. Okay. You can search inside this document and you see the detailed description. I'm not gonna to introduce this document, and I recommend you to have a look when you are trying to use it. Okay. Now, let's try to filter the data about the daily surface wind speed under SSP5 future scenarios. Okay, so we will use what we want. The variable is the surface wind speed. So the name in the climate model is SFC wind. So this is the standard name of the surface wind speed within the climate models. We will use this variable, and then the experiment, it will be SSP5 8.5 because we want future scenarios. Okay, so it's the experiment ID here. And then we want the daily wind speed. So we select the table ID as equal to day. And then we control all the initial condition as this one, because we want to make different models consistent by using the same initial conditions. So we define the member ID as this RIIIPIFI. So it represents one initial condition. Okay. Basically, we filter the previous exile by using this control sentence, and then we can see what happens about our filter data frame. Okay, we run this cell, you can see here we are. Now, what we got is that the activity from the scenario map, okay, the same as I introduced for the future scenarios. So it's the model into comparison for the different future scenarios. And then in this column, we will have the institution name. You can see here from the GFDL, it's in the America. In general, it produces 3 models here. Why we have 3 models here for this institution? Because first, it has 2 different grid labels. For sure, we can do some further filtering to make it consistent. We can remain only one of them. And then you can find this institution, they provide 2 different models. The first one is the GFDL CM4, and the other one is the GFDL ESM4. So even within one institution, they might have different climate models. And then all the experiment IDs for the same scenario, the high emission scenario, SSP5. And the time resolution is daily, and we look into the surface wind speed, okay? And we can also have a look of the different institution and different climate model. Okay, for this institution, you can find from Norway, they also have 2 different climate models. And also for CMCC, they have different climate models. Okay. And here, what we filter is all the available models which produce the future high emission scenarios with the daily wind speed. Okay, it's what all the available models within the data store in the Google API. And after we filter all of this, we can have a quick look. Like, okay, we will get 23 models from these models. And now, before we download all the models, we will make a function to make all the time axis of the models consistent. Because for these different models, there are always an issue. Because for different, you can imagine, for different institutions, they will have their different codes for the models. They will have different logicals when running the models, and the models inside have different equations, different ways to solve the equations, and also different parameter settings. And even the CMAP project, they give them a standard, like a standard protocol. There will be still some difference for different models. For example, some models, they name the variable in different ways. And some models, they have different grid resolution. And some models, they have different time axis because they have different format of the time axis. And it will cause problem when we're doing some further analysis. So the most straightforward way is to fix all the models into same time axis and the same grid resolution and also the same variable name. That is the most easier way to deal with all the different models. Okay, to deal with the time axis, we need to use a function here. So here is a function that I designed for you. You can, what we did is that we return a dataset with a fixed monthly date time 6/4. So this is a format of the time we will use from the start date to the end date. Because for the future scenarios in the climate models, they will start from 2015 January, and then some of the models, they even produce data longer than 2100, but we will keep them all consistent. So we let them end in 2100 in December. And then we read all the raw model and we use the CFT time because different models, they use different CFT times. We need to allow this option, otherwise it will cause some errors. And then we will select the time. Within the raw model, we select the start time and the end time. And then we will reassemble the models within a month. And then we replace all the CFT time index, because if you're dealing with this CFT index, there are several different formats of the time index. It will cause problem. And then we transform them all into a Panda datetime objective, okay? And after we transfer the new time steps, we reassign these new time steps to the raw climate model. And then we sort the values by the time range, and then we build the new dataset and return the new dataset. Okay, so we first run this function, because only if we run this function, we will be able to use the function. And then in the next step, we will try to use the links, like use the links here in our filtered data frame. So the links for our models to access their data by using the packages. So the packages, the GCS packages, it specifically deal with this kind of request. And we can request the distro. The distro is the link within our filtered data frame. Okay. So I think we can continue this part in our afternoon section to try to access all the climate data, all the climate model data, and then to do the analyze about the future wind speed in the Strait of Messina. Okay, and I will see you at 2 p.m. Let's see if there's an audience. No. Okay. See you later. Let's continue.